Welcome to Fictional Scientist. What you're about to hear won't change reality, but it may change how real it feels. If you fall asleep, that's part of the experience. You hear the clock ticking. It feels like it's moving forward, doesn't it? But physics says something disturbing. Uh, the universe has no preferred direction. Forward and backward are the same. If time were flowing backward, you would never know, because your memories would be rewritten with it. This moment you're living right now might not be your future, it could be your past. And after this video, you'll never hear a clock the same way again. The clock on the wall is ticking. Seconds, minutes, hours. Moving forward, always forward. But physics says something disturbing. The arrow of time is a choice, not a law. For the universe, there's no difference between forward and backward. So why do you always think you're moving forward? Maybe you're not. Let that sink in for a moment. The clock ticks. You hear it. Tick tock, tick tock. It sounds like progress. It sounds like a march toward the future. But what if that sound is a lie? What if the ticking is not taking you somewhere new, but replaying something that already happened? And the most disturbing part, you would never know. Close your eyes, take a breath, feel the weight of your body. You are here now in this moment. Or are you? Because if time can flow backward, if the universe doesn't care which direction the clock spins, then now be a very slippery concept. It becomes a trick your mind plays on itself to make sense of chaos. Think about this. Right now, as you're listening to these words, photons are hitting your retina. Sound waves are vibrating your eardrum. Chemical signals are cascading through your neurons. But all of this takes time to process. By the time your conscious mind registers now, that moment is already gone. You're always living in the past, experiencing a delayed broadcast of reality, about 80 milliseconds behind. So when you say now, what you really mean is 80 milliseconds ago. You are permanently trapped in the past, experiencing a world that has already moved on. Your entire life is a replay. Every moment you've ever experienced was already over before you experienced it. You've never truly lived in the present. You've only ever lived in the echo. Tonight, we're going to walk through the looking glass. We're going to examine the science that suggests time might not be what you think it is. We're going to question whether the past is behind you or whether it's being written right now, in this very second. We're going to explore the experiments that prove the future can influence the past. We're going to dive into the mathematics of entropy and discover why disorder might be the only real clock in the universe. And we're going to ask the most uncomfortable question of all. If time is reversible, if the universe can run backward just as easily as it runs forward, then what does that mean for you? For your memories? For your sense of self? For the story you tell yourself about who you are and where you're going? This is not a bedtime story to comfort you. This is a story to make you think, to make you question, to make you look at the clock on your wall and wonder, is it counting up or counting down? Is it measuring time or just measuring change? And is there a difference? Let's begin. And as we do, remember, every word you hear, every thought you have, every sensation you feel is already in the past by the time you notice it. You are not experiencing the present. You are experiencing a memory of something that just happened. So you are living in a permanent yesterday, chasing a tomorrow that might not exist, in a universe that doesn't care which direction you call forward. Welcome to the illusion of time. You trust the clock. Everyone does. It sits on the wall or wraps around your wrist, and it tells you where you are in the river of time. 8 a.m., time to wake up. Noon, time to eat. Midnight, time to sleep. The clock divides your life into neat little boxes, and you live inside them, comfortable, organized, moving forward. But here's the first crack in the illusion. The clock doesn't measure time. It measures change, the rotation of gears, the vibration of a quartz crystal, the decay of a cesium atom. These are processes, events, movements. The clock is just counting cycles. It's counting how many times something happens. But it's not measuring a river. It's not measuring a flow. Think about this carefully. When you say an hour has passed, what you really mean is the Earth has rotated 15 degrees, or my watch has completed 3,600 oscillations, or 9,192,631,770 cycles of radiation corresponding to the transition between two hyperfine levels of the ground state of cesium-133 have occurred. That last one is the actual definition of a second, by the way, established in 1967 by the International System of Units. A second is not a piece of time. It's a number of vibrations. It's a count of oscillations in an atomic system. You are not measuring the flow of a mysterious substance called time. You are counting waves in matter. And here's what that means. If you had a different kind of clock, one that counted different oscillations, you would get a different answer. If aliens visited Earth with clocks based on the vibration of hydrogen atoms instead of cesium, their seconds would be different from ours. Not wrong, just different. Because there's no universal clock, there's no cosmic metronome ticking away in the void, setting the tempo for reality. Every clock is arbitrary, every measurement is a choice. We chose cesium because it's stable, because it's precise, because the vibrations are consistent, but it's still just a counting device. It's still just measuring change, not time itself. Now let's go deeper. Let's look at what the laws of physics actually say about time, and what they say is shocking. Isaac Newton, in his Principia Mathematica, laid out the laws of motion. Objects in motion stay in motion. Force equals mass times acceleration. For every action, there's an equal and opposite reaction. These laws describe how things move through space, and crucially, they work exactly the same whether time is moving forward or backward. If you film a planet orbiting a star and play the video in reverse, you can't tell. The planet still follows Newton's laws. The orbit still makes sense. The equations are time symmetric. They don't have a preferred direction. The same is true for James Clerk Maxwell's equations of electromagnetism, published in 1865. Light waves, electromagnetic fields, the interactions between charges, all of it works the same forward and backward. You can reverse the direction of time in the equations, and they still describe valid physics. A light wave traveling backward in time is just as legitimate as one traveling forward. Even Albert Einstein's equations of general relativity, the pinnacle of our understanding of gravity and spacetime, are time symmetric. Black holes can swallow matter or they can spit it out. The math works both ways. The curvature of spacetime doesn't care which direction you call positive time. And then there's quantum mechanics. The Schrödinger equation, which governs the behavior of particles at the smallest scales, is completely reversible. You can run the wave function forward or backward, and it evolves according to the same rules. The future determines the past, just as much as the past determines the future. In fact, of all the fundamental laws of physics, only one breaks time symmetry. Only one equation has a built-in arrow, a preferred direction. And it's not a law of motion, it's not a law of forces or fields, it's a law of statistics. It's the second law of thermodynamics, and we'll get to that in a moment. But first, sit with this realization. The universe, at its most fundamental level, does not distinguish between past and future. The laws that govern reality are indifferent to the direction of time. To the universe, running forward and running backward are exactly the same. The equations don't care, the forces don't care, the fields don't care. So, why do you care? Why do you perceive a direction? Why does the world feel like it's moving forward and not backward? The answer is not in the physics of the universe. The answer is in the physics of you, in your brain, in your memory, in the biological machinery that constructs your sense of self. You are the one imposing a direction on a directionless universe. You are the one drawing the arrow on a clock that could tick either way. And once you understand that, once you see that the arrow is not out there but in here, everything changes. Let's talk about what time actually is, according to our best scientific understanding. In Einstein's theory of relativity, time is not a separate entity. It's not a river. It's not a dimension that exists independently of space. Time is a coordinate in a four-dimensional structure called space-time. Imagine a map. You have coordinates, latitude and longitude. These tell you where you are in space. Now add a third coordinate, altitude. Now you can describe any point in three-dimensional space. But in relativity, you need a fourth coordinate, time. A point in space-time is not just here. It's here, now. It's an event, a location in both space and time. And here's the crucial part. Just as north and south are not absolute directions, they depend on where you are on the globe. Forward and backward in time are not absolute either. They depend on your reference frame, your velocity, your position in a gravitational field. This was Einstein's revolutionary insight. Time is relative. It flows differently for different observers. If you're moving fast, time slows down for you relative to someone who's stationary. If you're near a massive object like a black hole, time dilates, stretching out. What feels like an hour to you might be years for someone far away. But if time can stretch and compress, if it can speed up and slow down, then it's not a universal river. It's more like a rubber band. And if it's a rubber band, then maybe it can snap, maybe it can twist, maybe it can loop back on itself. In fact, Einstein's equations allow for closed time-like curves, paths through space-time that loop back to their starting point in time. These are theoretical, yes. We've never observed one, but they're mathematically valid solutions to the equations. The universe doesn't forbid them. The laws of physics don't rule them out. What this means is that the universe, at its core, doesn't have a concept of past and future the way you do. It has events, it has coordinates, it has a structure, but the direction you travel through that structure is not predetermined. It's not carved into the fabric of reality. It's something you impose. It's something your consciousness projects onto the universe to make sense of it. And if that's true, then the question, is time flowing forward or backward, becomes less like asking, is the Earth rotating clockwise or counterclockwise, and more like asking, is north up or down? It's a matter of perspective, a matter of choice, a matter of how you choose to orient yourself in the structure. The clock on the wall is ticking, but it's not measuring time. It's measuring your journey through a four-dimensional landscape, and that journey might not be going in the direction you think. Let's talk about entropy. It's one of those words that gets thrown around a lot, often without a clear definition. But entropy is not complicated. It's actually very simple. Entropy is a measure of disorder, of randomness, of how many different ways you can arrange a system and still have it look basically the same. Imagine a deck of cards, fresh out of the box, sorted by suit and number, all the hearts together, all the spades together in perfect order. That's a low entropy state. There's only one way to arrange the deck to get that specific order. It's unique, it's organized. Now, shuffle the deck, now the cards are in a random order. This is a high entropy state. Why? Because there are millions of different ways to shuffle the deck, and almost all of them look random. There's only one perfectly sorted arrangement, but there are billions of shuffled arrangements. High entropy means many possible configurations. Low entropy means few possible configurations. The second law of thermodynamics, one of the most fundamental principles in all of science, says that entropy always increases in a closed system. Things naturally go from order to chaos, from unique to generic, from organized to random. Coffee cools down, ice melts, buildings crumble, stars burn out. The universe is slowly, inevitably, irreversibly sliding toward maximum disorder. This is not a theory. This is not a hypothesis. This is one of the most battle-tested, experimentally verified laws in physics. In over 150 years since it's been formulated, no one has ever observed entropy decreasing in a truly isolated system. Not once, not ever. And this is where your sense of time comes from. You don't feel time passing, you feel entropy increasing. You feel the universe decaying around you. The direction of time's arrow is simply the direction of increasing disorder. The past is the low entropy state. The future is the high entropy state. And you, right now, are surfing the wave of decay. To understand why entropy is so important, we need to talk about Ludwig Boltzmann, the Austrian physicist who revolutionized our understanding of thermodynamics in the late 19th century. Boltzmann realized something profound. Entropy is not about energy. It's about information. It's about probability. Boltzmann showed that entropy could be defined mathematically as the natural logarithm of the number of microscopic states that correspond to a given macroscopic state. In simpler terms, entropy measures how many different ways you can arrange the atoms in a system and still have the system look the same from the outside. Take a gas in a room. Macroscopically, you just see a gas evenly distributed, but microscopically, every single air molecule has a position and a velocity. There are trillions upon trillions of ways to arrange those molecules and still have the gas look evenly distributed. That's high entropy. But if all the gas molecules spontaneously gathered in one corner of the room, leaving a vacuum everywhere else, that would be low entropy. Why? Because there are very, very few arrangements of molecules that produce that result. It's highly specific, it's highly ordered. Boltzmann's insight was that the second law, entropy always increases, is not a law about energy or forces, it's a law about probability. Systems evolve toward high entropy states simply because there are more of them. It's statistically inevitable. You're not fighting a force, you're fighting statistics. Imagine you have a coin and you flip it a million times. The most likely outcome is roughly 50% heads and 50% tails. That's the high entropy state, maximum disorder, maximum random. But theoretically, you could get all heads. That's a low entropy state, perfectly ordered. But the odds of that happening are astronomically small. A number so large that if you wrote it out, it would have more digits than there are atoms in the observable universe. That's why entropy increases. Not because there's a force pushing it upward, but because there's nowhere else for it to go. The system is just exploring all possible states, and almost all of them are high entropy. Low entropy states are so rare, so improbable, that once you leave them, you're never coming back. And this statistical inevitability is what gives time its arrow. But here's where things get weird. If entropy always increases, if the universe is always moving from order to chaos, then that means in the past, the universe must have been more ordered than it is now. And if you keep going back further and further into the past, you eventually arrive at the Big Bang, the moment of creation, 13.8 billion years ago. And the Big Bang was an incredibly low entropy state. All the matter and energy in the universe concentrated in an unimaginably small region, in an almost perfectly smooth, uniform configuration. That's not just low entropy, that's absurdly, incomprehensibly, impossibly low entropy. Here's the problem. Why? Why did the universe start in such an ordered state? Why didn't it start in a high entropy state, a random, chaotic mess? That would be the most likely state, statistically speaking. A low entropy beginning is mind-bogglingly improbable. It's like flipping a coin a trillion times and getting all heads. This is called the past hypothesis, and it's one of the biggest unsolved problems in cosmology. We don't know why the Big Bang was low entropy. We don't have a good explanation. We can't derive it from first principles. We just observe it and accept it as an initial condition, a boundary condition for the universe. But it's deeply unsatisfying because without that low entropy starting point, the arrow of time doesn't make sense. Entropy can only increase if it starts low. If the universe began in a high entropy state, entropy would already be at maximum, and there would be no arrow, no flow, no sense of past and future. So the direction of time, the thing that feels most fundamental, most obvious, most undeniable, rests on a mystery. It rests on the unexplained fact that the universe started ordered and has been decaying ever since. Some physicists speculate that the Big Bang was not the true beginning. Maybe the universe existed before in a high entropy state, and the Big Bang was just a fluctuation, a statistical accident, a rare dip in entropy. If that's true, then the arrow of time we experience is local, not universal. It's just the direction that happens to correlate with our particular fluctuation. And in other parts of the multiverse, in other fluctuations, the arrow might point the opposite way. There might be entire universes where time flows backward, where entropy decreases instead of increases, where effects precede causes. And the beings in those universes, if they exist, would think they're moving forward, just like you do. Because forward is always defined by the direction your memories point. Now, here's a question that should keep you up at night. Can entropy decrease? The second law says no. In a closed system, entropy can only increase or stay the same. It can never decrease. That's what makes the arrow of time irreversible. But the second law is a statistical law, not an absolute one. It describes what happens on average over large numbers of particles over long periods of time. It doesn't forbid entropy from decreasing. It just makes it incredibly unlikely. Think back to the gas in the room. If you wait long enough, and we're talking about timescales so long they make the age of the universe look like a blink, there will be a random fluctuation. The molecules bouncing around chaotically will, purely by chance, all end up in one corner of the room. Entropy will decrease. The system will move from disorder to order. This is not a violation of the second law. This is the second law. It says entropy tends to increase, but it allows for brief, temporary decreases. These are called fluctuations, and they happen all the time on small scales. A few molecules might cluster together, a tiny region of space might cool down slightly. These are blips in the upward march of entropy. But on large scales, over long times, these fluctuations average out. The overall trend is always upward. Entropy increases, order decays. The universe marches toward heat death. But here's the disturbing implication. If fluctuations are possible, if entropy can briefly decrease, then time locally can run backward. For the duration of the fluctuation, the arrow of time reverses. The gas gathers instead of spreading. The coffee warms up instead of cooling down. Cause and effect flip. And if you were inside the fluctuation, if you were a conscious observer made of the same molecules that were fluctuating, you wouldn't notice. Your memories would be part of the fluctuation. Like they would point in the direction of the local entropy gradient. You would still experience time as flowing forward, even though from an external perspective, it was flowing backward. This is the nightmare scenario, the possibility that time's direction is not absolute, not universal, but local and contingent, that it can flicker, wobble, reverse, and you would never know. And it gets worse, because the most efficient way for a conscious observer to spontaneously appear in a high entropy universe is not through billions of years of evolution. It's through a single massive fluctuation that creates a brain, complete with false memories, for a brief instant before dissolving back into chaos. This is the Boltzmann brain paradox, and we'll come back to it later. But for now, just sit with this realization. Entropy is the only thing giving time a direction. And entropy is just a statistic, and statistics can lie. Let's talk about memory. You trust your memory. It tells you who you are, it tells you where you've been, it tells you that yesterday happened before today. But here's a fact that neuroscientists have known for decades, but most people don't want to hear. Every time you remember something, you're not replaying a recording, you're reconstructing it. You're building it from scratch. And every time you build it, you change it. Your brain does not work like a video camera. It doesn't capture a perfect copy of an event and store it in a file. Instead, it extracts key features, emotions, context, a few vivid details, and discards the rest. When you later recall that memory, your brain takes those fragments and fills in the gaps. It invents details. It borrows from other memories. It uses your current emotional state and knowledge to make the story make sense. This is not a bug. This is a feature. Your brain evolved to be efficient, not accurate. Perfect recall would require enormous amounts of storage and processing power. So instead, your brain compresses, it summarizes, it creates a nerve that's good enough to guide your behavior, even if it's not perfectly faithful to what actually happened. Neuroscientist Elizabeth Loftus has spent her career demonstrating just how unreliable memory is. In one famous study, she showed participants a video of a car accident. Afterwards, she asked them, how fast were the cars going when they smashed into each other? A week later, she asked if they remembered seeing broken glass at the scene. About a third said yes, but there was no broken glass in the video. The word smashed primed them to imagine a more violent crash, and their brains filled in details that never existed. In another study, Loftus convinced people they had been lost in a shopping mall as a child. She used a combination of false photos, suggestive questioning, and encouragement from family members. About 20-25% of participants developed detailed emotional memories of an event that never happened. They remembered the fear, they remembered what the mall looked like, they remembered being reunited with their parents. All of it was false. All of it was constructed. This is terrifying. It means your memories are not evidence of the past. They're stories your brain tells itself in the present to explain the patterns of activation in your neurons. And stories change every time they're told. Here's an experiment you can try right now. Think of a vivid memory from your childhood. Maybe a birthday party, a family vacation, a moment at school. Picture it in your mind. Notice the details, the colors, the sounds, the people. Now ask yourself, is this memory real? How do you know? You might say, I remember it. I was there. But that's circular reasoning. You're using memory to validate memory. You might say other people remember it too. But their memories are just as unreliable as yours. They might be confabulating just like you are. You might say, I have photos. True. But photos only capture a fraction of a second. The rest of your memory, the emotions, the context, the before and after, is filled in by your brain. And every time you look at the photo, you reinforce the constructed narrative, making it feel more real. Here's the uncomfortable truth: you have no direct access to the past. The past is gone, it's inaccessible, it doesn't exist anywhere you can reach. What you call the past is actually a mental model you've constructed in your brain right now, in this moment, to explain the current arrangement of neurons in your head. Think about what this means. The past is not a fixed record. It's a dynamic construct. It's constantly being revised, rewritten, updated. Every time you remember something, you change it slightly. And the next time you remember it, you're remembering the changed version, not the original. Over time, your memories drift further and further from what actually happened. And here's the most disturbing part: you can't tell the difference. A constructed memory feels exactly like a real one. The vividness, the emotional intensity, the sense of certainty, these are not reliable indicators of accuracy. In fact, studies show that the most confident memories are often the most distorted. Your brain is not trying to preserve the truth, it's trying to maintain a coherent narrative. And if the truth doesn't fit the narrative, the brain edits the truth. It's not lying to you exactly. It's just prioritizing consistency over accuracy. It's choosing the story that makes the most sense given your current beliefs, emotions, and identity. This is why eyewitness testimony is so unreliable. This is why conspiracy theories spread so easily. This is why people can be absolutely convinced of things that never happened. The feeling of remembering is not proof that the memory is real. It's just proof that your brain has constructed a convincing story. Now let's connect this back to time. If the past is constructed by your present moment brain, then the direction of causation is backward. The present is creating the past, not the other way around. You think the past caused the present. You think that what happened yesterday is the reason things are the way they are today. But that's only half true. Yes, the physical universe evolved according to the laws of physics. The atoms in your brain today are configured the way they are because of the atoms yesterday and the day before, and all the way back to the Big Bang. But the story you tell yourself about that evolution, the narrative you construct to explain why you are who you are, that's being created right now, in this moment, by your current brain state. The past you remember is not the past that actually happened. It's the past your brain thinks should have happened to lead to the present. This is not just philosophy, this is neuroscience. Studies using fMRI scanners show that when you recall a memory, the same brain regions activate as when you imagine a future scenario. Remembering and imagining use the same neural machinery. They're both constructive processes, both creative acts. In other words, your brain doesn't distinguish between remembering the past and imagining the future. It treats them both as simulations, as models, as stories. The only difference is the label. One story is tagged past, the other future, but the process of generating them is the same. This means that your sense of having a history, of having come from somewhere, is not fundamentally different from your sense of going somewhere. Both are narratives constructed in the present to orient you in time. And if the present is constructing the past, then the past is not fixed. It's fluid, it's negotiable, it's constantly being rewritten. Let's take this to its logical extreme. If your memories are unreliable, if they're constantly being rewritten, then who are you? Your sense of self is built on memory. You think you're the same person you were yesterday because you remember being that person. You think you're the same person you were as a child because you have memories connecting you to that child. But if those memories are constructed, if they're stories rather than recordings, then the continuity of your identity is an illusion. You're not the same person you were yesterday. You're a new person with a set of memories that convince you you're the same person. Think about this. Every cell in your body is replaced over time. Your skin cells are replaced every few weeks. Your liver cells every few months. Even your neurons, once thought to be permanent, are now known to undergo significant changes throughout your life. The physical matter that makes up your body is not the same matter it was 7 years ago. So what makes you you? Not your body. That's constantly changing. Not your thoughts. Those are different every moment. The only thing that seems to provide continuity is memory. But if memory is unreliable, if it's a story rather than a record, then the continuity of your identity is a story too. It's a narrative your brain tells itself to create a sense of coherence, of consistency, of self. And here's the kicker: you're not just the author of that story, you're also the main character. You're simultaneously writing the script and acting it out. You're creating your past and living your present at the same time. And the past you create shapes the present you experience, which in turn shapes the past you create next time. It's a feedback loop, a self-referential system. And in that system, the question what really happened becomes meaningless. Because what really happened is whatever your brain decides happened. And your brain decides based on what makes the best story, what fits the narrative, what supports your identity. So when you ask, is time flowing forward or backward? Maybe the answer is neither. Maybe time isn't flowing at all. Maybe you're just generating a sequence of stories, each one claiming to remember the previous one and calling that sequence time. You are not traveling through time. You are a story being told, and the story is telling itself. Now we need to move from psychology to physics, from the unreliability of memory to the actual, measurable, experimentally verified weirdness of the universe. Because there's a phenomenon in quantum mechanics that suggests the future can influence the past. It's called retrocausality. And it's not speculation, it's been proven in the lab. You've probably heard of the double slit experiment. It's the most famous demonstration of quantum weirdness. Here's how it works. You take a particle, an electron, a photon, anything small enough to exhibit quantum behavior, and you fire it at a barrier with two slits. Behind the barrier is a detector screen that records where the particle lands. If the particle is a particle, like a tiny ball, you'd expect it to go through one slit or the other and create two bands on the screen. But that's not what happens. Instead, you get an interference pattern, a series of bright and dark bands that can only be created by a wave passing through both slits simultaneously and interfering with itself. So the particle is acting like a wave. It's going through both slits at once. That's weird, but physicists got used to it. They called it wave-particle duality and moved on. But then they tried something clever. They decided to put a detector at the slits to see which one the particle actually went through. And the moment they did that, the interference pattern disappeared. Suddenly, the particle was acting like a particle again. It went through one slit or the other, not both. The act of observation changed the outcome. This is the observer effect. The particle seems to know whether it's being watched. If you watch it, it behaves one way. If you don't, it behaves another way. And this isn't a matter of the detector physically disturbing the particle. Even if you use a detector that doesn't touch the particle, that doesn't interact with it in any traditional sense, the result is the same. Observation matters. Now, physicist John Archibald Wheeler, one of the giants of 20th century physics, asked a question that should make your head spin. What if you don't decide whether to observe until after the particle has already gone through the slits? This is called the delayed choice experiment. The setup is this. The particle is fired, it passes through the slits, it's already traveling toward the detector screen, but before it hits, you randomly decide whether to measure which path it took or not. Common sense says it shouldn't matter. The particle already went through the slits. Its path is already determined. Your future decision can't change what already happened, but quantum mechanics says otherwise. If you decide to measure the path, the particle behaves as if it went through one slit. The interference pattern disappears. If you decide not to measure, the particle behaves as if it went through both slits. The interference pattern appears. And here's the crucial part. The particle responds to your future choice. Its behavior in the past changes based on a decision you make in the future. The future reaches backward and rewrites the past. This is not theoretical. This has been done multiple times in multiple variations. The results are consistent and undeniable. The future can influence the past. Let's go even deeper. There's a variation of this experiment called the quantum eraser, first performed in the late 1990s. It's even more disturbing. In this version, you don't just decide whether to measure the path. You decide whether to erase the information about the path after the particle has already been detected. You let the particle hit the screen, you record which slit it came through. The event is over. The past is past. But then, after the fact, you choose to erase the record. You destroy the information about which slit it used. And when you do that, the interference pattern reappears, not in the future, in the past. The data you already collected shows an interference pattern when you sort it by the cases where you erase the information. It's as if the particle went back in time and changed its behavior, as if your future action of erasing the information reached backward and told the particle, you weren't measured. Go ahead and interfere with yourself. This has profound implications. It means the past is not a fixed record. It's a probability distribution that remains open, fluid, negotiable until the information about it is finalized. And finalized doesn't mean occurred. It means measured and recorded in a way that can't be undone. Until that happens, the past exists in a state of quantum superposition, multiple conflicting histories coexisting simultaneously, and your actions in the present determine which history becomes real. Now, there's a mathematical framework that makes sense of all this. It's called the two-state vector formalism, developed by physicists Yakir Aharonov and Lev Weidman. The idea is this: the state of a quantum system is not just determined by its past, it's also determined by its future. Think of it like a rope stretched between 2 points. One end is the past boundary condition, the initial state. The other end is the future boundary condition, the final measurement. The rope is under tension from both ends. The state of the system now is the result of both the past pushing forward and the future pulling backward. In this framework, causation is bidirectional. The present is caused by the past and the future simultaneously. Events are not just consequences of what came before, they're also consequences of what comes after. This sounds insane. It violates everything we think we know about how the world works, but it makes accurate predictions. It explains the results of delayed choice and quantum eraser experiments. It's mathematically consistent, and so far, no experiment has contradicted it. If this is true, if the future genuinely influences the past, then the arrow of time is a lie. The past is not before the future in any causal sense. They're both boundary conditions on the present. They both shape what happens now, and neither one is more real or more fixed than the other. This idea has a name in philosophy: teleology. It's the doctrine that things are shaped not just by efficient causes, but by final causes. For centuries, science rejected teleology. It was seen as mystical, unscientific, a relic of Aristotelian thinking. But quantum retrocausality brings teleology back, not in a mystical sense, but in a rigorous mathematical sense. The future state acts as an attractor. It pulls the present toward it, and in doing so, it shapes the past. Think about your life. You make decisions based on your goals, your desires, your vision of the future. You take actions today because of where you want to be tomorrow. In a sense, your future self is reaching backward, guiding your present self. Usually, we think of this as imagination, as planning, as projection. But what if it's more than that? What if your future, in some quantum sense, is already there, already real, and already pulling you toward it? What if the reason you feel drawn to certain paths, certain choices, is because those paths lead to a future that's already trying to manifest? This is not fate, it's not predestination. The future isn't fixed, but it's not open either. It's probabilistic. There are many possible futures, each with its own weight, its own likelihood, and all of them are reaching backward, pulling on the present, trying to make themselves real. You're not being pushed from behind by the past. You're being pulled from ahead by the future, and the tension between these two forces, the past that was and the future that wants to be, is what creates the experience of now. And if that's true, then maybe time isn't a line. Maybe it's a web, a network of causes flowing in both directions, forward and backward, creating a tangled self-referential loop where every moment is both cause and effect, both past and future, both determined and determining. You are not moving through time. You are the knot where past and future intersect. And the tighter the knot, the more real you feel. Let's step back and look at the big picture, because there's a view of time that emerges directly from Einstein's theory of relativity, and it changes everything. It's called the block universe, or eternalism. Here's the core idea. Time is not a flowing river. Time is a dimension, just like space. And just as all points in space exist simultaneously, Your house exists at the same time as the Eiffel Tower, even though they're in different locations. All points in time exist simultaneously. Your birth exists. Your death exists. This moment, right now, exists. All of them, all at once, frozen in a four-dimensional block. Imagine a loaf of bread. The bread is space-time. Each slice is a moment in time. Your childhood is one slice, your death is another. This exact moment is somewhere in the middle. But here's the key. All the slices exist simultaneously. The loaf doesn't move, it doesn't flow from past to future. It just is, eternal, unchanging, complete. In the block universe, the past has not ceased to exist. It's still there, frozen in its slice. The future has not failed to arrive. It's already there, frozen in its slice. You, right now, are simply a particular slice of the block that happens to be experiencing itself as now. This is a direct consequence of Einstein's special relativity. In 1905, Einstein showed that simultaneity, the concept of now, is relative. Two observers moving at different speeds will disagree about which events are happening at the same time. One observer might see event A happening before event B. Another observer moving at a different speed might see B happening before A. This is not a trick of perception. This is not about signal delay. These observers genuinely, objectively disagree about the order of events. And if they disagree, then there is no universal now. There is no moment that all observers agree is the present. And if there's no universal now, then the distinction between past, present, and future is not a feature of the universe. It's a feature of your perspective, your reference frame, your point of view. It's subjective, not objective. It's a local phenomenon, not a cosmic one. Einstein himself understood the implications of this. In 1955, when his lifelong friend Michel Besso died, Einstein wrote a letter to Besso's family. In it, he said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Think about what he's saying. Besso isn't gone. He's still there in his slice of the block, living his life in the moments that are past from Einstein's perspective, but are just as real, just as present as the moment Einstein was in when he wrote the letter. Besso's death is not the end of Besso. It's just the boundary of his worldling, his path through the block. And that boundary exists now, always, eternally. This is both comforting and terrifying. Comforting because it means nothing is ever truly lost. Everything that ever happened is still happening somewhere in the block. Your childhood is still there, your first kiss, your happiest moment, all of it preserved forever in the eternal structure of space-time. But terrifying because it means nothing ever changes. You're not growing, you're not progressing. You're not moving toward anything. You're a static pattern in the block, frozen forever in your particular configuration. The story of your life is not being written. It's already written, all of it, from beginning to end. And you're not the author, you're a character, a fixed character in a finished book. But if the block universe is real, if all moments exist simultaneously, why does it feel like time is flowing? Why do you experience a present moment that seems to be moving, progressing, leaving the past behind, and approaching the future? The answer, once again, is entropy. Your brain is a physical system subject to the second law of thermodynamics. Your memories are stored as physical patterns in your neurons, configurations of proteins, synapses, electrical activity. And those patterns are correlated with low entropy states in your past and high entropy states in your future. So you experience time as flowing from low entropy to high entropy, from past to future, from order to disorder. But this is not the universe flowing. This is your brain, a local subsystem, interpreting the static structure of the block through the lens of increasing entropy. Think of it like reading a book. The book is complete. All the pages exist simultaneously, but you read them one at a time, in order. The early pages have certain words. The later pages have different words. As you read, you move through the book, experiencing the story unfolding. But the story isn't unfolding. It's already there. All of it. Your experience of reading, of moving through the narrative, is just your consciousness moving through a static structure. Your life is the same. The you at age 5 and the you at age 50 both exist in the block in different slices. But your consciousness, whatever that is reading through those slices, experiencing them one at a time in order of increasing entropy. And because your memories are encoded in the neurons of each slice, each you thinks it's the current you experiencing the present moment. The flow of time is not the universe moving, it's your awareness moving. Or perhaps not even moving. Perhaps your awareness is also static, and the sensation of flow is just an artifact of how memories are encoded in the structure of your brain. This raises the most unsettling question of all. If the block universe is real, if the future is already there, already written, then what happens to free will? In the block universe, your choices are already made. The moment where you decided to listen to this story is sitting there in space-time, frozen, eternal. And the moment where you decide to stop is also sitting there, fixed and unchanging. You're not creating the future, you're discovering it. You're walking through a museum exhibit that's already been curated. This is hard determinism, and it seems to eliminate freedom. If all your decisions are already encoded in the structure of the block, if the future is fixed, then you can't change anything. You're just following a script that was written before you existed, or rather, that was always written in the eternal present of the block. But here's the paradox. Even if your choices are predetermined, even if the future is fixed, you still experience the sensation of choosing. You still deliberate, you still feel the weight of decisions, you still regret past choices and hope for better future ones. The subjective experience of free will persists, even if the objective reality is deterministic. Why? Because your consciousness is embedded in the block. You're experiencing it from the inside. From inside a static structure, looking at the branches of your world line, it feels like you're choosing which branch to take. But in reality, all the branches already exist. You're not choosing which path to create, you're choosing which path to notice, which path to identify with. Your sense of agency is not an illusion in the sense of being false. It's real. It's a genuine feature of how your consciousness interacts with the structure of the block. But it's not what you think it is. You're not the author of your story. You're the reader. And the paradox is that the reader is also a character in the story, reading about themselves. You are simultaneously the observer and the observed, the subject and the object, the one who chooses and the choice being made. And in that paradox, in that strange loop, lies the only kind of freedom available in a block universe. The freedom to experience, to witness, to be aware of the structure you're embedded in. You can't change the block, but you can illuminate it with your consciousness. And that illumination, that awareness, is the closest thing to freedom there is. We need to make a crucial distinction now. There are actually two different arrows of time, and they're not the same thing. There's the thermodynamic arrow, the direction of increasing entropy, and there's the psychological arrow, the direction your consciousness seems to move from past to future, from memory to anticipation. Most of the time, these two arrows point in the same direction. That's why time feels so consistent, so unidirectional. But they're conceptually separate, and in principle, they could decouple. The thermodynamic arrow is rooted in physics. It emerges from the statistical behavior of large numbers of particles. It's the direction that correlates with increasing disorder, with the spreading out of energy, with the approach toward equilibrium. This arrow is real, measurable, and universal. The psychological arrow, on the other hand, is rooted in information and memory. It's the direction that correlates with the accumulation of records, with the encoding of experience, with the asymmetry between remembering the past and not remembering the future. This arrow is local, subjective, and tied to the existence of conscious observers with memory systems. Now here's the key insight. The psychological arrow follows the thermodynamic arrow because memories are physical records, and physical records are low entropy structures. To record information, you have to create order. You have to organize matter in a specific, non-random way. And creating order locally requires increasing disorder globally. So the act of forming memories always points in the direction of increasing entropy. That's why you remember the past and not the future. Not because the past is before the future in some absolute sense, but because the low entropy structure of your memories correlates with the low entropy past of the universe. But what happens in a fluctuation? Remember, entropy can decrease temporarily due to random chance. In a small region of space for a brief period of time, the thermodynamic arrow can reverse. Disorder can decrease. The system can move from high entropy to low entropy, and if a conscious observer existed in that region during that fluctuation, its psychological arrow would follow the local thermodynamic arrow, would point backward in time relative to the rest of the universe. From the outside, we would see this observer's memories forming in reverse. It would remember the future and be surprised by the past. Its causal reasoning would be inverted. What we call effects, it would call causes, and vice versa. But from the inside, from the observer's perspective, everything would feel normal. It would feel like time was flowing forward because forward is defined by the direction of memory, and memory is defined by the local entropy gradient. The observer would never know its arrow was reversed. It would construct narratives about its past, make plans for its future, and experience the flow of time just like we do. This is deeply unsettling. It means that the directionality of time is not a property of the universe, it's a property of subsystems within the universe. And different subsystems, in principle, could have different arrows, could experience time flowing in opposite directions. And neither one would be wrong. Both would be correct from their own perspective. Imagine a goldfish with a 30-second memory span. Every 30 seconds, the goldfish forgets everything. It has no long-term memory, no sense of history, no continuity of self. From the goldfish's perspective, each 30-second interval is its entire life. It has memories going back 30 seconds, and those memories create a sense of past, of having existed before this moment. But those memories are, at most, 30 seconds old. Now imagine the goldfish is not in a flowing river of time, but in a static block universe. There are trillions of goldfish moments, each frozen in space-time, each with a different 30-second memory span. The goldfish moment at time t1 remembers the last 30 seconds. The goldfish moment at time t2 remembers a different last 30 seconds, and so on. To each goldfish moment, it feels like time is flowing. It feels like it has a past and is moving toward a future. But in reality, there's no flow. There's just a collection of static goldfish moments, each with its own memory, each convinced it's experiencing the passage of time. You are the goldfish. Your memory span is longer, hours, days, years, but the principle is the same. You are a static pattern in the block universe, with memories that point backward toward lower entropy and anticipations that point forward toward higher entropy. You feel like you're flowing through time because your memories create that sensation, but you're not flowing. You're a fixed point in a fixed structure, experiencing the illusion of motion. And here's the kicker. There's no way to step outside your own head and check. You can't look at yourself from the outside. You can't verify that you're moving or static. All you have is your subjective experience, your memories, your anticipations, your sense of now. And all of those are internal to you, part of the system, part of the illusion. Um, the question, is time really flowing, is unanswerable because the only tool you have to answer it is your own experience of time, which is the thing you're trying to verify. It's circular, self-referential. You're using the system to measure the system, and the system is designed to produce the output, yes, time is flowing, regardless of whether it actually is. You're trapped in the goldfish universe, and the walls of your aquarium are made of memory. Now let's ask the truly disturbing question. Could you be living backward right now and not know it? Imagine the universe reaches a maximum entropy state, heat death. Everything is uniform, random, dead. Then, purely by chance, a massive fluctuation occurs. Entropy decreases, order emerges, and in that pocket of order, structures form: atoms, molecules, planets, stars, life, brains. But here's the thing, that fluctuation is temporary. Entropy will increase again, the order will decay, and from the perspective of an external observer watching the whole process, the fluctuation would look like a bubble of reverse time. The thermodynamic arrow would point backward during the fluctuation. And if a conscious observer existed in that bubble, with memories encoded in the direction of the local entropy gradient, it would experience time flowing forward toward higher entropy. But what it calls forward would be backward from the external perspective. So you could be in one of those bubbles right now. The universe could have reached maximum entropy billions of years ago from an external perspective, and You could be a temporary fluctuation, a brief eddy in the sea of chaos, experiencing time in reverse. What you call the Big Bang could be the future, not the past. What you call heat death could be the past, not the future. You could be living backward and you would never know. Because backward and forward are labels you assign based on memory, and memory always points in the direction of increasing entropy within your local system. Even if that direction is opposite to the global arrow, even if the whole universe is watching you run in reverse, you would still feel like you're moving forward. This is the ultimate paranoia, the ultimate epistemic vertigo. The realization that you have no way of knowing, no possible test, no anchor in reality that could tell you which direction you're actually moving in time. All you have is your memory, and memory can lie. Let's talk about the Boltzmann brain paradox. It's named after Ludwig Boltzmann, the physicist who gave us statistical mechanics and the concept of entropy. And it's one of the most disturbing ideas in modern cosmology. Here's the setup. We know the universe is expanding. We know entropy is increasing. If the current trend continues, the universe will eventually reach a state of maximum entropy, a heat death. All the stars will burn out. All the black holes will evaporate. All that will be left is a vast, cold, empty void filled with low-energy photons and a uniform distribution of particles. But even in that void, quantum fluctuations will continue. Virtual particles will pop in and out of existence. And given enough time, infinite time, those fluctuations will occasionally create larger structures. A hydrogen atom, a molecule of water, a protein, and eventually, through sheer random chance, a brain. Not a brain attached to a body, not a brain that evolved through billions of years of natural selection, just a brain. A disembodied, spontaneously fluctuating brain, complete with neurons firing, memories encoded, thoughts occurring, a Boltzmann brain. And here's the problem. It's vastly, overwhelmingly, cosmically more likely for a single Boltzmann brain to fluctuate into existence than for an entire universe to evolve through the Big Bang, star formation, planet formation, abiogenesis, and billions of years of evolution. Why? Because of entropy. Creating an entire universe with stars, planets, and evolved life requires an enormous amount of low entropy initial conditions. It requires the Big Bang to start in a highly ordered state and then evolve through 13.8 billion years of increasing disorder. That's a specific, narrow path through probability space. It's incredibly unlikely. But a Boltzmann brain, that's just a random fluctuation. It doesn't require a Big Bang. It doesn't require stars or planets. It just requires atoms to randomly arrange themselves into the pattern of a functioning brain for a brief instant before dissolving back into chaos. And statistically, that's much easier. The math is brutal. If the universe lasts forever and quantum fluctuations continue forever, then for every real, evolved observer like you, there will be an infinite number of Boltzmann brains. The ratio approaches infinity, which means, statistically speaking, you are almost certainly not an evolved biological organism. You're almost certainly a Boltzmann brain that spontaneously fluctuated into existence in the void, complete with false memories of a life that never happened. Think about what this means. A Boltzmann brain doesn't just pop into existence blank. That would be unlikely too. The most likely configuration is a brain with memories already encoded, because there are more ways to arrange atoms into a brain with memories than into a brain without memories. It's a matter of probability. So the Boltzmann brain appears in the void, fully formed, with neurons firing, with a complete set of memories about a childhood that never happened, a family that never existed, a world that was never real. It remembers going to school, falling in love, having breakfast this morning. None of it happened. It's all false. But to the brain, it feels absolutely real. And here's the truly disturbing part. You have no way of knowing you're not a Boltzmann brain right now. Every memory you have could be a random pattern of neural activity that spontaneously appeared in the void 1 second ago. This video, this voice, this entire story about time and entropy, all of it could be a false memory implanted in a brain that has only existed for a fraction of a second. You might object, but I can verify my memories. I can check them against external records. I can ask other people. But those external records, they're part of your sensory experience. They could be part of the fluctuation too. The piece of paper, the photograph, the other person, all of it could be part of the illusion. Your entire world could be a simulation running in a randomly assembled brain that's about to dissolve back into the quantum foam. There's no test you can perform, no experiment, no observation, because any test you perform, any evidence you gather is itself part of your experience, part of the pattern of your brain state. If your entire brain is a fluctuation, then all the evidence you could possibly gather is also a fluctuation. It's all internal to the system. There's no external reference point. This is solipsism taken to its logical extreme. Not just I can't prove other minds exist, but I can't prove anything exists, including my own past, including the stability of my present, including the likelihood that I'll exist in the next second. Cosmologists hate the Boltzmann brain paradox. It undermines everything. If we're probably Boltzmann brains, then we can't trust our observations of the universe. We can't trust our scientific theories. We can't trust that the laws of physics we've discovered are real because they might just be part of the false memories in a random brain. Some physicists argue that the paradox is a reductio ad absurdum, a proof by contradiction. The reasoning goes, if our cosmological model predicts that we're probably Boltzmann brains, and we know we're not Boltzmann brains because, well, we just know, then our cosmological model must be wrong. We need to revise our theories until they predict that evolved observers like us are more likely than Boltzmann brains. But this response is circular. How do we know we're not Boltzmann brains? We assume it. We take it as a given, but the whole point of the paradox is that we count the difference. A Boltzmann brain would also think it's not a Boltzmann brain. It would also have reasons, memories, evidence that support its existence as a real evolved being. The conviction that you're real doesn't prove you're real. Other physicists propose that the universe won't last forever, that the expansion will reverse, or that vacuum decay, which we'll discuss later, will destroy the universe before Boltzmann brains can form. But these are desperate measures. They're inventing new physics specifically to avoid the conclusion that we're probably Boltzmann brains. The truth is, we don't have a good solution to this paradox. It's an open wound in cosmology, a crack in the foundation. And the more you think about it, the worse it gets. So how do you live with this? How do you go about your day knowing that you might be a Boltzmann brain, that your entire life might be a 1-second hallucination, that everything you remember might never have happened? The honest answer is you assume you're not. You take it on faith. Not religious faith, but pragmatic faith. The faith that allows you to function, to make plans, to care about things. Because the alternative, taking the Boltzmann brain hypothesis seriously, is paralyzing. It's nihilistic. It's the end of meaning. If you're a Boltzmann brain, then nothing you do matters. You'll dissolve in the next instant. There's no future to plan for. There's no past to learn from. There's just this moment, this flickering of false consciousness, and then nothing. But here's the thing. Even if that's true, even if you are a Boltzmann brain about to dissolve, this moment is still all you have. This experience, this awareness, this sensation of being, it's still real to you. It's still the only reality you've ever known or ever will know. And in that sense, it doesn't matter whether you're a Boltzmann brain or an evolved organism. Your experience is your experience. Your suffering is real suffering. Your joy is real joy. The ontological status of your existence doesn't change the phenomenological reality of your consciousness. So you make a choice. You choose to believe you're real. You choose to believe your memories are accurate. You choose to believe the future exists and that your actions matter. Not because you can prove these things, you can't, but because believing them allows you to live, to function, to find meaning in the absurdity. This is existentialism meeting cosmology. This is the ultimate leap of faith. Not faith in God, but faith in the continuity of your own existence. Faith that the next moment will come. Faith that you are who you remember being. Faith that the universe is more than a random fluctuation in the void. And maybe that faith is enough. Maybe it has to be. Because the alternative is the void, and the void is waiting. Let's return to quantum mechanics and dig deeper into why it treats time as reversible. The fundamental equation of quantum mechanics is the Schrödinger equation, formulated by Erwin Schrödinger in 1926. It describes how the wave function, the mathematical object that contains all the information about a quantum system, evolves over time. And here's the key. The Schrödinger equation is completely time reversible. If you have a wave function at time t1, you can use the Schrödinger equation to calculate what it will be at time t2 in the future. But you can also run the equation backward, calculating what the wave function was at time t0 in the past. Both directions are equally valid. The equation treats past and future symmetrically. This is fundamentally different from classical physics, where friction, air resistance, and other dissipative forces make most processes irreversible. But in quantum mechanics, at the level of the wave function, there's no dissipation, no friction, no loss. The evolution is unitary, a fancy word meaning information is preserved and the process can be reversed. This has profound implications. It means that at the quantum level, there's no arrow of time. A particle moving forward in time is mathematically equivalent to an antiparticle moving backward in time. Richard Feynman made this explicit in his diagrams. You can interpret an electron moving from point A to point B in the future as equivalent to a positron moving from B to A in the past. It's the same mathematical description, just with the time coordinate flipped. But there's a catch. The Schrödinger equation describes how the wave function evolves when the system is isolated, when it's not being measured or observed. But when you make a measurement, something different happens. The wave function collapses. It goes from a superposition of multiple possibilities to a single definite outcome. And this collapse is not described by the Schrödinger equation. It's a separate postulate of quantum mechanics. And unlike the Schrödinger equation, the collapse is not reversible. Once the wave function collapses, you can't uncollapse it. The information about all the other possibilities is lost. The superposition is destroyed. This is the measurement problem, one of the deepest mysteries in quantum mechanics, and it's intimately connected to the arrow of time, because measurement creates an irreversible record. It creates a memory, a trace, a piece of information about what happened. And information, as we've seen, is tied to entropy. Creating a record increases entropy. So measurement, by creating a record, by collapsing the wave function, is the moment when the quantum world connects with the thermodynamic arrow of time. Before measurement, the quantum system is time reversible. It exists in a superposition, exploring all possibilities simultaneously. But after measurement, after the collapse, the system has a definite past, it has a history, it has an arrow. The act of observation is what breaks the time symmetry, what transforms the timeless quantum realm into the time-directed classical realm. There's an alternative interpretation of quantum mechanics that preserves time symmetry even through measurement. It's called the many worlds interpretation, proposed by Hugh Everett in 1957, and it's both elegant and terrifying. In the many worlds interpretation, the wave function never collapses. Instead, when a measurement occurs, the universe splits. Every possible outcome of the measurement happens, but in different branches of reality. You measure the spin of an electron. In one branch of the universe, you get up. In another branch, you get down. Both branches are real, both exist, but they can't interact with each other. They've decohered, separated, become independent. From your perspective, you only see one outcome. You see up and think the wave function collapsed. But that's because you are now in the branch where up happened. There's another version of you in the other branch seeing down, thinking the same thing. Neither of you is wrong. You've both measured correctly. You're just in different branches of the multiverse. In this interpretation, the wave function is still following the Schrödinger equation. It's still evolving unitarily, reversibly, without any collapse. The appearance of collapse is just your subjective experience of being in one branch rather than all branches simultaneously, and this preserves time symmetry. The multiverse as a whole is still reversible. If you could somehow reverse the wave function of the entire multiverse, you'd retrace all the branchings, all the measurements, all the way back to the beginning. The arrow of time, in the many worlds view, is not a fundamental feature of quantum mechanics. It's an emergent feature of being a localized observer in one branch of the wave function. But this comes at a cost, the cost of accepting that every time you make a decision, every time a quantum event occurs, the universe splits. There are now countless versions of you, each in a different branch, each experiencing a different history, and they're all equally real. You are not one person, you are a vast, branching tree of people, most of whom you will never meet, all of whom think they're you. There's one more piece of quantum physics we need to discuss: CPT symmetry. This is one of the most fundamental symmetries in physics, and it connects time reversal to other transformations. CPT stands for charge conjugation, parity reversal, and time reversal. The CPT theorem, proven in the 1950s, states that all physical laws must remain unchanged under the combined operation of all three transformations. What this means is that if you take any physical process, swap all particles with their antiparticles c, flip the spatial coordinates p, and reverse time t, you get another valid physical process. The laws of physics are symmetric under this combined transformation. But here's the interesting part. You can think of antiparticles as particles moving backward in time. An electron moving forward in time with positive charge is equivalent to a positron moving backward in time with positive charge. They're two different descriptions of the same underlying reality. John Wheeler and Richard Feynman took this idea seriously. They proposed the one-electron universe thought experiment. What if there's only one electron in the universe and it's moving back and forth in time, tracing out an incredibly complex path that intersects our time slice multiple times? When it's moving forward in time, we see it as an electron. When it's moving backward in time, we see it as a positron. This is probably not literally true. The number of electrons and positrons in the universe doesn't match, for one thing. But it illustrates a deep point. At the quantum level, the distinction between past and future is not as clear-cut as we think. Particles can, in a sense, move backward in time. And if particles can do it, if the fundamental constituents of matter don't respect the arrow of time, then why should we expect macroscopic objects like ourselves to have a well-defined direction? The answer, always, comes back to entropy. Macroscopic objects have entropy because they're made of many particles. And many particles means statistics. And statistics means the second law. And the second law means the arrow of time emerges not from the behavior of individual particles, but from their collective behavior. You are not a particle, you are a statistical ensemble. And that's what gives you an arrow. We need to zoom out now, way out. Let's think about the universe as a whole. Because the arrow of time is not just a local phenomenon, it's a cosmic phenomenon. And it all traces back to one fact. The universe began in a state of extremely low entropy. The Big Bang, 13.8 billion years ago, was not a chaotic explosion. It was the opposite. It was highly ordered, highly structured, with matter and energy distributed almost uniformly across space. The temperature was uniform to within 1 part in 100,000. This is low entropy. This is a very special, very unlikely state. Since then, the universe has been expanding, cooling, and increasing in entropy. First, matter clumped together due to gravity, forming stars and galaxies. This seems like it's creating order, but remember, gravity is weird. For gravitational systems, clumping increases entropy, not decreases it. A uniform distribution of matter has lower entropy than a clumpy one when gravity is involved. Stars burned, fusing light elements into heavier ones. Planets formed. Life emerged. All of this is a consequence of the universe starting in a low entropy state and evolving toward higher entropy. The arrow of time that you experience, your memories, your aging, your sense of past and future, is riding on the coattails of this cosmic evolution. But why? Why did the Big Bang start with low entropy? This is the past hypothesis, and it's the greatest unsolved mystery in cosmology. We have no explanation. We can't derive it from more fundamental principles. We just observe it and accept it as an initial condition. Some physicists speculate that there might be a deeper explanation. Maybe there's a law of nature we don't know about that requires the universe to start with low entropy. Maybe the Big Bang was preceded by a previous universe that underwent a bounce, and the bounce naturally creates low entropy. Maybe our universe is part of a vast multiverse, and only the low entropy pockets can support observers like us. So we necessarily find ourselves in one of those pockets, anthropic principle. But none of these ideas are proven. They're speculations, attempts to explain the one fact that makes the arrow of time possible. The universe started ordered, and it's been decaying ever since. If entropy always increases, then eventually the universe will reach a state of maximum entropy. This is called heat death, and it's the ultimate fate of our cosmos if current cosmological models are correct. Here's how it happens. Stars will continue to burn through their fuel. Over trillions of years, all the hydrogen in the universe will be fused into heavier elements. Stars will die, becoming white dwarfs, neutron stars, or black holes. Galaxies will drift apart due to the accelerating expansion of space. Eventually, even black holes will evaporate through Hawking radiation, a process that takes billions of years or more. What's left? A cold, dark, empty universe. The temperature everywhere will be just a fraction of a degree above absolute zero. Matter will be spread so thin that interactions between particles will become vanishingly rare. The universe will be in a state of thermodynamic equilibrium. Maximum entropy, perfect uniformity, no gradients, no flows of energy, no ability to do work. And in that state, time, as we experience it, will cease to exist. Because time is the perception of change. Time is the observation of systems evolving from low entropy to high entropy. But when entropy is at maximum, when there's nowhere left to go, there's no change. The universe becomes static, frozen, not in temperature, but in configuration. It's reached the end of its evolution. This doesn't mean the universe is destroyed, the particles are still there, the space is still there, but nothing happens. No stars form, no life emerges, no thoughts occur. The universe continues to exist, but in a dead, unchanging state that will persist for eternity. This is the true end. Not a bang, but a whimper. Not destruction, but stagnation. The ultimate victory of entropy over order. The final triumph of decay. But there's a twist. In recent decades, cosmologists have developed a model called eternal inflation, and it changes the picture dramatically. The idea is that the early universe underwent a period of exponentially rapid expansion called inflation. This is well established. But in the eternal inflation model, this inflation never completely stops. In most of the universe, inflation continues forever, exponentially expanding, but in some regions, inflation stops, and those regions become bubble universes like ours, where stars and galaxies can form. Each bubble universe has its own Big Bang, its own low entropy starting point, its own arrow of time. And crucially, new bubbles are constantly forming in the eternally inflating space between them. The multiverse as a whole is in a state of eternal expansion, eternally creating new universes with new low entropy beginnings. This solves the past hypothesis problem in a sense. Our Big Bang wasn't the beginning of everything, it was just the beginning of our bubble. The low entropy wasn't special or unlikely. It's a natural feature of a bubble universe budding off from the eternally inflating background. But it creates new problems. If eternal inflation is real, then there are infinitely many bubble universes, each with its own laws of physics, determined by how quantum fields settle into their vacuum states in that bubble, each with its own arrow of time. Some might have arrows pointing in the same direction as ours, others might have arrows pointing in different directions. Some might not have arrows at all. And if bubbles are constantly being created, then even in our own universe's far future, after heat death, new bubbles could form, new Big Bangs could occur, new civilizations could arise. The story doesn't end with heat death, it just pauses, and then it starts again, somewhere else, in a new bubble. Time on the scale of the multiverse becomes fragmented. There's no universal clock, no cosmic now, just a vast, eternally expanding space filled with bubbles of time, each one a self-contained story with its own beginning, middle, and end. There's another speculative model worth mentioning, Roger Penrose's conformal cyclic cosmology, CCC. Penrose is a Nobel Prize-winning physicist, and his model is radical. He proposes that the heat death of our universe is not the end. Instead, when the universe reaches maximum entropy, when all matter has decayed and only massless radiation remains, it undergoes a mathematical transformation. The infinite future becomes the Big Bang of a new universe cycle, a new aeon. The key insight is that in a universe with only massless particles, photons, there's no way to measure scale. A universe that's infinitely old and infinitely large is, in a certain mathematical sense, equivalent to a universe that's infinitely small and just being born. Penrose exploits this equivalence to stitch the end of one aeon to the beginning of the next. If CCC is correct, then the universe is eternal. But it's not eternally stuck in heat death. It's eternally recycling. Each aeon begins with a Big Bang, evolves through stars and galaxies and life and heat death, and then transforms into the Big Bang of the next next aeon. The cycle repeats forever, and crucially, the arrow of time resets with each cycle. Each aeon has its own arrow, pointing from its own Big Bang toward its own heat death. But the arrows don't necessarily point in the same cosmic direction. From a perspective outside the cycles, if such a perspective makes sense, time might loop or branch or form some more complex structure. Penrose even claims there's evidence for CCC in the cosmic microwave background radiation, circular patterns that could be the imprint of gravitational waves from the previous aeon. Other cosmologists are skeptical. The evidence is debated, but the idea is fascinating. Time is not a single line from beginning to end. Time is a cycle, or perhaps a spiral. Each turn through the cycle creates a new universe, a new arrow, a new opportunity for entropy to increase and create the conditions for life, consciousness, and the illusion of progress. We've circled around this question long enough. Let's address it directly. Does consciousness play a special role in quantum mechanics? Does the act of observation by a conscious mind cause the wave function to collapse? This is the von Neumann-Wigner interpretation, named after physicist Eugene Wigner. The argument goes like this. In quantum mechanics, a system remains in superposition until it's measured. But what counts as a measurement? If you use an instrument to measure an electron, the instrument becomes entangled with the electron. The whole system, electron plus instrument, is now in superposition. If you then look at the instrument, your brain becomes entangled with the instrument. Now the system is electron plus instrument plus brain, all in superposition. If someone else looks at you, they become entangled. Where does it end? Where does the chain of entanglement stop and collapse occur? Wigner's answer: at consciousness. The wave function collapses when the information enters a conscious mind. Because consciousness is non-physical, or at least not fully described by quantum mechanics, it acts as an external observer that can't be entangled. It's the thing that looks without becoming part of what it's looking at. This is deeply controversial. Most physicists reject it. They argue that consciousness is just another physical process, that there's nothing special about brains that exempts them from quantum mechanics. They point to decoherence, the process by which quantum systems interact with their environment and effectively collapse without any conscious observer. But Wigner's interpretation has one thing going for it. It solves the measurement problem. It gives a clear answer to the question, when does collapse occur? The answer is when a conscious observer looks. Everything else is relative, subjective, entangled. Only consciousness stands outside the quantum web. Remember the delayed choice quantum eraser experiment? The one where your future decision seems to change the past behavior of a particle? Some physicists have suggested that consciousness plays a key role here too. The argument is subtle. In the delayed choice experiment, the particle's behavior depends on whether information about its path exists or has been erased. But existence of information is a tricky concept. Information exists only relative to an observer. A piece of paper with data on it is just atoms arranged in a pattern. The information is the interpretation of that pattern by a conscious mind. So when you erase the information, what you're really doing is ensuring that no conscious mind can ever extract it. You're not destroying atoms, you're destroying the possibility of knowledge. And it's that possibility or impossibility that determines how the particle behaves in the past. If this interpretation is correct, then consciousness is not just observing time, it's participating in the construction of time. Your future conscious decision about what to know and what not to know reaches backward and helps determine what actually happened. This makes consciousness not just an observer, but a co-author of reality. Not in a mystical sense, but in a rigorous quantum mechanical sense. The universe is a participatory universe, as John Wheeler called it, and your consciousness is one of the participants. But this raises an even deeper question. What is consciousness? How does a physical system like a brain give rise to subjective experience, to the feeling of what it's like to be you? This is the hard problem of consciousness, formulated by philosopher David Chalmers. And the hard problem has a temporal dimension. Your experience of consciousness is not static. It's not a photograph. It's a flow, a stream. William James called it the stream of consciousness. You experience yourself as moving through time, as having a continuous existence that persists from moment to moment. But why? If the block universe is real, if all moments exist simultaneously, then why do you experience yourself as moving? What creates the flow? One possibility. Consciousness is the process of information integration. Your brain is constantly taking in sensory data, combining it with memories, predicting the future, and creating a unified model of your situation. This process takes time. It unfolds, it has a direction, from input to integration to output. And that direction, that unfolding, creates the sensation of flow. You feel like you're moving through time because your consciousness is a process, and processes have temporal extent. They take time. They evolve from earlier states to later states. But here's the strange part. The direction of that evolution is determined by entropy. Your brain forms memories by creating low entropy structures. It predicts the future by extrapolating high entropy trends. The flow of your consciousness always points from past to future because it's following the thermodynamic arrow. If your brain could somehow operate in reverse, if it could form memories of the future and have amnesia about the past, then your subjective experience would also reverse. You would experience time flowing backward, but you wouldn't know it because backward and forward are defined by your experience. So consciousness doesn't just observe the arrow of time. Consciousness is the arrow of time, at least subjectively. The flow you feel is not the universe moving, it's your brain processing, integrating, predicting, remembering. It's the machinery of thought itself, which operates in the direction of increasing entropy. There's a scientific theory of consciousness that connects these ideas. Integrated Information Theory, IIT, developed by Giulio Tononi. IIT proposes that consciousness is identical to integrated information. A system is conscious to the degree that its parts are interconnected and interdependent. A single atom has almost zero integrated information. Its state doesn't depend on the states of other atoms, but a brain has enormous integrated information. Every neuron is connected to thousands of others. The state of the whole system is vastly more than the sum of its parts. And crucially, integrated information has a temporal dimension. Your brain doesn't just integrate information spatially, it integrates information temporally. Your experience right now is not just a snapshot. It's an integration of recent past, present perception, and anticipated future. This temporal integration is what creates your sense of continuity, your sense of being a self that persists through time. You're not experiencing a series of disconnected moments. You're experiencing a temporally extended pattern of information integration. And that pattern has a direction. It integrates from past to present to future because that's the direction of causation in a thermodynamic universe. The past affects the present through memory, the present affects the future through action, but not vice versa because information flows down the entropy gradient. So your subjective experience of time is not a passive observation of the universe flowing. It's an active process of your consciousness integrating information across time in the direction determined by entropy. You are creating the flow by being conscious. Without consciousness, without information integration, there would be no flow. Just a static block of moments, frozen and meaningless. You are the flow, and the flow is you. Let's get practical. If time can flow backward, if entropy can temporarily decrease, if the arrow of time is not absolute, then can we detect it? Can we build an experiment that would tell us if we're moving backward through time? The short answer is probably not. Because any experiment we design uses our memory and our causation, both of which are defined by the local entropy gradient. If we're in a fluctuation where time is locally reversed, our experiments would still make sense to us. They would still show causation flowing from past to future, even if those labels are reversed from an external perspective. But there are some subtle tests we could try. One idea, look for violations of the second law of thermodynamics on small scales. We know entropy can decrease in small systems for brief periods due to fluctuations. If we observe a system long enough, we should see occasional decreases. In fact, this has been done. In 2002, physicists at the Australian National University observed a microscopic bead in water. They tracked its position for long periods and found that occasionally, purely by chance, the bead would move against the expected thermal gradient. It would spontaneously absorb energy from its surroundings and move uphill, so to speak. Entropy decreased. The second law was violated briefly as predicted by statistical mechanics. These violations are rare and short-lived, but they prove that entropy can decrease. And during those brief moments, the local arrow of time is reversed. Of course, the bead doesn't experience this reversal. It's not conscious. But if there were a tiny conscious observer living on the surface of the bead, it would experience those moments as normal. It would construct memories in the direction of its local entropy gradient, and it would feel like time was flowing forward, even though it was actually flowing backward relative to the rest of the universe. Another practical application, quantum computers. These machines exploit quantum superposition and entanglement to perform calculations that classical computers can't. And crucially, they exploit the time symmetry of quantum mechanics. In a quantum computer, quantum bits can be in superpositions of 0 and 1 simultaneously. The computation proceeds by manipulating these superpositions through unitary operations, time-reversible transformations that preserve information. At the end, you measure the qubits, collapsing them into definite values. But here's the interesting part. You can, in principle, run a quantum computation backward. If you carefully record all the operations you performed, you can reverse them, and the system will return to its initial state. The computation is reversible. You can uncompute just as easily as you compute. This is impossible in classical computing, where information is constantly being erased, heat dissipation, the Landauer limit we discussed earlier. But in quantum computing, as long as you don't measure the system, as long as you don't allow it to decohere, the evolution is perfectly reversible. Some researchers have proposed using this reversibility to explore retrocausality. If you could carefully isolate a quantum system, manipulate it in the future, and see if those manipulations affect measurements made in the past, you'd have direct evidence of backward causation. So far, these experiments are speculative, but the technology is advancing rapidly. Quantum computers are, in a sense, machines that exploit the fact that the universe doesn't care about the direction of time. They operate in a regime where past and future are symmetric, where calculations can flow backward as easily as forward. They're time machines, not in the sense of letting you visit the past, but in the sense of performing operations that treat time as a dimension to be navigated rather than a flow to be endured. On a larger scale, cosmologists are searching for evidence that the arrow of time is not universal. One intriguing possibility: if there are regions of the universe where entropy is decreasing due to massive fluctuations or due to different initial conditions, we might be able to detect them. How? By looking for anomalies in the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB is remarkably uniform, but it has tiny fluctuations, regions that are slightly hotter or cooler than average. These fluctuations are the seeds of structure in the universe, the regions that eventually became galaxies and clusters. But what if some of those fluctuations are not seeds, but scars? What if they're the imprint of regions where time is flowing backward? Such regions would appear to us as sources of order rather than disorder. They would seem to be creating structure rather than destroying it. Penrose, in his conformal cyclic cosmology, claims to have found such signatures in the CMB, circular patterns that he interprets as gravitational waves from the previous aeon, from a universe that ended before ours began. Other cosmologists dispute this interpretation. The patterns could be statistical flukes, or they could be explained by more conventional physics. But the search continues, and it's not impossible that we could find evidence of time-reversed regions, either in the CMB or in the large-scale structure of the universe. If we do, it would be the most profound discovery in the history of science. It would prove that the arrow of time is not absolute, that the universe contains pockets where entropy decreases, where effects precede causes, where the future reaches back to shape the past, and it would confirm what physics has been hinting at for a century. Time is not what we think it is. But let's be honest. Even if we find these anomalies, even if we build perfect quantum computers, even if we observe entropy decreasing in the lab, we'll never be able to prove that we're not, right now, in a time-reversed region. Because any test we perform, any observation we make, is interpreted through the lens of our memory. And memory always points in the direction of the local entropy gradient. If we're in a reversed region, our memories would also be reversed, and we would interpret all our observations as consistent with normal forward time. This is the fundamental limit of knowledge about time. You can never step outside your own temporal perspective. You can never observe time objectively from a viewpoint external to time itself. You're embedded in time. You're part of the flow or part of the illusion of flow. And that embedding, that participation, makes objective knowledge impossible. This is not a failure of science, it's a feature of reality. Some questions don't have answers, not because we're not smart enough, but because the questions themselves are based on false assumptions. The question, is time really flowing forward or backward, assumes there's an objective fact of the matter, a God's eye view from which the direction can be determined. But there's no such view. There's only your view, my view, the view from within. And from within, time always flows in the direction your memories point, which the question is not answerable. Not because we lack the tools, um, but because the question is asking about something that doesn't exist. An objective, universal, observer, independent arrow of time. The arrow is always relative, always local, always tied to consciousness, to memory, to entropy. And that makes it real subjectively, but not real objectively. It's the ultimate user interface, the most fundamental illusion, the lie that makes existence possible. So where does this leave you? You've followed the argument, you've seen the evidence, you understand that time might not be flowing, that your memories might be unreliable, that the past might not exist, that you might be a Boltzmann brain, that consciousness might be creating, not observing the flow of time, and you're lying there in the dark and you're thinking, what now? How do I live with this? How do I get up tomorrow and go about my day knowing that everything I think I know about time is probably wrong? The weight of this knowledge is heavy. It's vertigo-inducing. It's the feeling of the floor dropping out from under you. You thought you were standing on solid ground. The past happened, the future is coming, time is flowing, and now that ground has turned to mist. But here's the thing, that ground was always mist. You were always floating, you just didn't know it. And now that you know, now that you've seen through the illusion, you have a choice. You can despair or you can adapt. Despair says nothing matters. If time is an illusion, if the past is constructed, if I might be a Boltzmann brain, then my life is meaningless. My choices are meaningless. My relationships are meaningless. Everything is just a flickering of false consciousness in the void. But adaptation says the illusion is all there is. If time is a construction of my consciousness, then my consciousness is what makes time real. If my memories are unreliable, they're still my memories. They're still the only access I have to my past, my identity, my sense of self. If I might be a Boltzmann brain, then this moment, this experience right now, is all I have, and it's precious precisely because it might be fleeting. The existentialists understood this. Camus, Sartre, Kierkegaard. They grappled with the absurdity of existence, the lack of inherent meaning, the weight of freedom. And they concluded, you must create your own meaning. You must choose to live, to act, to care, even in the face of absurdity. The same applies here. You must choose to believe in time, even if time is an illusion. You must choose to trust your memories, even if they're unreliable. You must choose to act as if the future exists, even if it's already written in the block. Not because these beliefs are true, you can't prove they're true, but because they're necessary. They're the foundation of action, of care, of meaning. Let's be pragmatic. Even if the block universe is real, even if all moments exist simultaneously, you still experience time as flowing. You still move through your life moment by moment, making decisions, forming relationships, pursuing goals. The subjective experience of time is undeniable, even if the objective reality is uncertain, and that subjective experience is what matters for living. When you wake up tomorrow, you'll remember yesterday. You'll plan for the day ahead. You'll interact with people based on shared memories and mutual expectations. All of this requires treating time as flowing, treating the past as fixed, treating the future as open. Does it matter that objectively in the block universe, your future is already determined? Not really, because you don't have access to that future. You don't know what's written in the later slices of the block. So from your perspective, from your embedded in time subjective viewpoint, the future is genuinely unknown. You have to make choices as if they matter. because to you they do matter. They shape your experience, your trajectory through the block, your journey from low entropy to high entropy. In other words, you can accept the scientific truth that time might not be what it seems while still living as if it is. This is not hypocrisy. This is wisdom. It's recognizing that subjective and objective truth are of different categories and that your life is lived in the subjective realm, not the objective. Objective truth says the block universe is eternal and unchanging. Subjective truth says I experience myself as moving through time, and that experience is real for me. Both can be true simultaneously. They're not contradictory, they're complementary. Here's a silver lining to all this uncertainty. If time is not what you think, if the flow is an illusion, then the present moment becomes more important, not less. Think about it. If the past is just a construction of your current brain state, then the only thing you really have is now. If the future is uncertain or already determined, then the only thing you can influence, the only thing that's truly alive, is this moment right now. The clock is ticking, but the tick is not the universe moving forward. The tick is you, waking up to a new slice of the block, a new configuration of atoms, a new moment of consciousness. And in that moment, you're free. Free to choose how to interpret your memories, free to choose how to anticipate your future, free to choose what to do, what to think, what to care about. This is the gift of recognizing time's illusory nature. It shifts your focus from past and future, both of which are, in a sense, constructions, to the present, which is the only thing that's immediately, viscerally, undeniably real. You can regret the past, but the past you're regretting might not have happened the way you remember. You can fear the future, but the future you're fearing might not exist yet, or might already be determined. But the present is here, it's happening, you're in it, and that's the only fact you can truly verify. Mindfulness practices, meditation, the concept of being present, these are all ways of recognizing this truth. They're methods for shifting your attention from the narrative of time, past, present, future, to the experience of time, this moment, this breath, this sensation. And when you do that, when you fully inhabit the present, the question, is time flowing forward or backward, becomes irrelevant. Because you're not in the flow, you're in the now, and the now is timeless. Ultimately, living with uncertainty about time requires courage. The courage to act without knowing, the courage to care without certainty, the courage to build a life on foundations that might be shifting or might not exist at all. This is not a new problem. Philosophers have grappled with it for millennia. Descartes doubted everything, trying to find one indubitable truth. He concluded, I think, therefore I am. I am. But even that is shaky. Maybe you're not thinking. Maybe thinking is happening and you're just the illusion it creates. Maybe there's no I at all. But you can't live in that level of skepticism. You can't function if you doubt the existence of everything, including yourself. So you make assumptions, you accept certain beliefs as working hypotheses, and you live as if they're true, even though you can't prove them. This is faith, not religious faith, but existential faith. Faith in the continuity of your existence, faith in the reliability of your senses and memories, faith in the existence of other minds, of external reality, of causation, of time. And maybe that's okay. Maybe faith in this sense is not a weakness, but a strength. It's the ability to act decisively in the face of uncertainty. It's the willingness to commit to a belief, to a course of action, to a way of being, even when you know you can't prove it's correct. You make a leap. You choose to believe you're not a Boltzmann brain. You choose to believe your memories are roughly accurate. You choose to believe time is flowing forward, not because the evidence compels you, but because these beliefs enable you to live a meaningful life. And in the end, that's what matters. Not whether time is really flowing, but whether you can flow through your experience of time with grace, with purpose, with awareness. Not whether the past really happened, but whether you can learn from your memories. Not whether the future is open or determined, but whether you can act with intention and care. The universe might not care about time, but you do, and that's enough. The clock on the wall is still ticking. You can hear it even now, even after everything we've discussed. Tick, tock, tick, tock. The sound that seemed so simple at the beginning of this journey now carries a weight of ambiguity. Is it ticking forward? Is it ticking backward? Is it ticking at all? Or is it just you moving through a static block, illuminating one moment at a time with the flashlight of your consciousness? You don't know. You can't know. And maybe that's the point. The mystery of time is not a problem to be solved. It's a feature of existence to be experienced. The uncertainty is not a bug in your understanding. It's a fundamental aspect of what it means to be a conscious temporal being. You are time, not in the sense that you control it or create it, but in the sense that you embody it. Your consciousness is the place where the timeless block becomes a lived experience. Your memory is the mechanism that creates the arrow. Your attention is the spotlight that makes now feel real. Without you, the universe is just a mathematical structure, a four-dimensional block of matter and energy, frozen and meaningless. But with you, with any conscious observer, the universe wakes up. It experiences itself, becomes aware of its own structure, its own beauty, its own mystery. And in that awakening, time is born, not as an objective feature of the cosmos, but as a subjective feature of consciousness. Time is what it feels like to be aware, to remember, to anticipate, to care. The clock on the wall is ticking, but the meaning of that ticking, the direction, the significance, the very reality of it is something you create, moment by moment, thought by thought, experience by experience. You are the author of your time, not because you control the universe, but because your consciousness is the lens through which the universe becomes temporal. You are the interpreter, the translator, the bridge between the timeless structure and the temporal experience. And that is a profound responsibility. But it's also a profound gift because it means you're not passive. You're not a victim of time. You're a participant, a co-creator, a partner in the dance between entropy and memory, between past and future, between the block and the flow. So embrace the uncertainty. Accept that you might never know whether time is really flowing. Accept that your memories might be unreliable, that your sense of self might be constructed, that the universe might be running backward and you'd never know. Accept it all, and then choose to live anyway, choose to care anyway, choose to act as if your choices matter, as if your relationships are real, as if the future is worth building toward, because even if it's all an illusion, it's your illusion. It's the only reality you have, and that makes it precious. That makes it worth protecting, worth celebrating, worth living fully. The clock on the wall is ticking, and you're here to hear it, and in the end, that's all that matters. Close your eyes, take a breath, feel the weight of your body. You are here, now, in this moment. Or maybe you're not. Maybe you're in a different moment, reading backward, constructing a past that never happened, but it doesn't matter because wherever you are, whenever you are, you're experiencing something. You're aware, you're conscious, you're alive, in whatever sense alive means in a universe where time might be an illusion. And that awareness, that consciousness, that experience, it's the only truth you need. The clock is ticking, but you don't have to listen. You don't have to worry about which direction it's ticking. You just have to be, and you are. That's enough. Sleep well.